Well, after discussing about the thermodynamic driving force for diffusion, let us move into the how the diffusion happens, the mechanisms. You know, there are two approaches to study diffusion. One which is known as continuum theory. This is what we are more used to it. It takes care of the average movement of a collection of large number of atoms. When you have a large number of atoms moving from one phase to other phase, we just take care of average movements. That means we need to know average velocities of these atoms. And we always make observation at the macro scale. Very easy to apply Fick's law, which we will see now, because this is continuum. We are considering the whole system to be continuous. But you know, actually speaking, atoms do not move like a flock of birds moving in the sky. Okay, atoms moves by jumps, and because when the birds are flying, they are moving at a continuous pace with certain fixed velocity. Sometimes they will accelerate or decelerate, but they will move. So you can always define an average velocity very easily. But atoms do not. They actually are thermally activated, and they actually move by jumps. So therefore, we need to know also what is the microscopic theory of the of the motions of the atoms, if we really want to know what actually happenings to that. So first we will discuss the continuum theory. Why is diffusion? That is earlier I have discussed, transport of atoms because of the thermally activated jumps, and reason is basically thermodynamics. This is will tell you what actually happens. Suppose this is taken from the book of Diffusion in Solids by Paul Schumann, and this is, suppose I have particular element of atoms. You see here 1, 2, 3, 4 atoms, and there is a central black atoms, and there is another 4 atoms, but central atom is missing. That means there is a void there. So now this atom, a black atom, wants to jump, wants to move actually from here to there. That is what is discrete jump. Discrete means one step, but it is not like a play that we can simply jump over a barrier and reach, like high jump or a long jump. Here it will happen in steps. So when this species will try to jump from here to there, it will go to a saddle point. As you see here, this is saddle point. Saddle point means the atom will be in between these two grey color atoms, and if the sizes are different, obviously sizes will be different, and the space available here in between these two grey color atoms is not sufficiently large enough to accommodate these black atoms. So the black atom will push these grey color atoms. Now that means it requires a certain amount of a barrier to cross, because pushing requires energy, and that is what is shown here. So once it pushes these two atoms, it crosses this barrier and then reaches this position here very easily. So that means diffusion happening in discrete steps. First step is that atom moves from here to this position, then it pushes these atoms, second step, and finally it reaches from here to there. In the whole process, atom moves from A point to B point. A and B both are the low energy configurations, as you see here on the curve, but it also goes through a barrier, okay. Just like in Olympics people have hurdle race. So somebody is coming, there is a hurdle, it jumps over the hurdle and reaches the point B. So atom is actually doing that. Atom actually passing through a barrier, or basically jumping over the hurdles and reaching the point B. So this is how actually atomic jump happens in a regular species. This is microscopic picture of the system. Now let us do it for a couple of collection of atoms. That is one atom, and what is known as the interdiffusion. Interdiffusion means from one part to the other part. Suppose initially I have two, again taken from Callister, because this represents so nicely written there. You can see here this is one color of atoms. Let us suppose this is A type, and there is another color of atom here on the right side, it is called B type. And if I plot the concentration profile, in this region is 100% A, in the region 100% B. So, therefore, here to here there is 0% A, here to there is a 0% B. That is what you see here. So, what happens if I just allow at some temperatures from some time? What will happen? Obviously, some B atoms will move from the right side to the left side, some atoms will move on the left side to the right side. That is what is down the concentration gradient. And if it moves, there will be a range in which intermixing will happen. You see here, this is where all are A atoms, this is where almost all are B atoms. Okay, this is where almost all are B atoms, and this is a range where you have mixed between A and B together. That is why we call interdiffusion, because they are intermixed. So, this layer is what is the diffusion zone actually we call, because that is why the intermixing is happening. Now, if you plot the concentration gradient, what will happen? It is completely A here till this point, it is completely B here till this point, and in between these two you have a mixture of A and B. Now, this diffusion zone will slowly expand, they will move from this position to this A side, this position to the B sides. This is what is microscopically will happen, and it is understandable. But each time this collection of atoms moving from A side to B side or vice versa, the process which I discussed with you here will happen. So, that means each atom will pass through a barrier, diffusion barrier, and things will happen like that way. So, in an alloy, I would say very nicely that atoms tends to migrate from regions of high concentration region to low concentration region, but does not matter the high or low, it is basically the construction which I have drawn in the last class is basically tells you it is happening down the chemical potential gradient. Now, let us look at few interesting stuffs. Does it mean that if I have only A atoms in the system, there will be no diffusion? Well, that is not the correct answer. You can always have self diffusion. Like if I have pure copper, still copper atom from one point can diffuse to other point. That is mainly because there will be always a vacancy. There is always some finite number of vacancies present at any temperature above absolute 0. So, because of these vacancies, atoms can diffuse. So, here actually let us label some atoms like A, B, C, D. Now, what happened you see here? You see here after some time A atom has moved from here to somewhere in the left side of myself, D atom is moving right side, C atom is moving the left side, B atom moving the right side. That is obviously haphazard and random because it depends on availability of the vacancies, atoms will move. Now, basically what I am telling you for the last few minutes that atoms do move from one part to other parts, but obviously movement requires presence of the vacancies. That is exactly I showed you at the beginning when I showed you the diffusion barrier. So, vacancy is the most important vacancy diffusion is the most important diffusion mechanism in these materials, and here there is a vacancy you see here, this is atom is missing here. So, therefore, this atom can move here, this atom, this atom, this atom, this atom, this atom, any atoms can move depending on the who has the sufficient energy to cross that barrier. Now, these vacancies only apply to substitutional type atoms. Okay. Here we are talking about atoms are almost similar sizes, that means they can only sit in the lattice positions, they cannot sit in the interstitial positions. Here the rate will depend on number of vacancies present and obviously the activation energy to cross that barrier which I shown you few minutes back. Now, we can also have see here that these are the diffusions happening, as this black arrow shown the atom has diffused from here to there. So, vacancy has moved also. So, if the vacancy moves, then another atom can move into the vacancy. So, another configuration of atom will happen, the vacancy has moved above. So, basically diffusion can be also treated as a movement of vacancies. Vacancies moving from here to there, and in the process atoms are also interchanging their positions. Okay. Many situations possible. But similar situation is not true when you have interstitial atoms like carbon in steel, okay, or boron in a nickel aluminum alloy. Atomic size is very small, so but they will be sitting in the interstitial positions. Interstitial position means in between these lattice positions there will be interstitial position like octahedral void, tetrahedral voids. I already told you, again taken from Callister. As you see here, the atoms actually the interstitial position atoms at the beginning was at these positions and then it has moved there. For the interstellar atom to move, you do not need vacancies. Vacancies are present all throughout the system because these are the voids. So, there were large number of voids automatically present, and only thing remain is that this atom needs to push these two atoms and reach here. Okay, that is what needs. So, that obviously this atom also needs to pass through a barrier, but suppose the sizes of these atoms are very big. So, the void size is big, then what will happen? This size is enough, the void size is much enough for the atom to smooth movement of the atom from this position to this position, but that is not the always case. There will be always the sizes available here will not be sufficient enough for the small atom to move. So, there will be always some pushing is required, and this pushing leads to diffusion barrier. But whatever the reason, this diffusion by interstellar atom is much faster, in fact order of magnitude faster than the substitution atom diffusion, because of the availability of large number of vacant positions and the size of the smaller atom. Okay, so now you got an idea, because we cannot discuss diffusion in few lectures, we need to wind up somewhere. You got an idea that diffusion happens by atomic movements. That is what is the microscopic picture of diffusion. Now let us put it into mathematical form. Mathematical form in the sense, mathematical form of equations. So, whenever you talk about movement of atoms, we need to talk in terms of flux. Flux means number of moles diffusing per unit time per unit surface area, and because flux is a vector, so therefore it must have directions. So, whenever we talk about flux, we always assume, suppose unit area like this is an unit area, and we assume diffusion happens direction perpendicular to this surface area. So, that means if I have atoms here, they are moving through this area in the direction perpendicular to this area and certain times. So, the flux is basically given by these moles per unit area per unit time. So, that means this is unit of kg per meter square second, because or it is a moles per centimeter square second or moles per meter square per second. It will be either mole or kg, the mass or number of atoms, whatever it is, you can weigh, you can define. So, this can be measured very nicely. Remember, this is a measurable quantity. Flux can be easily measured. You can make a thin film of known surface area, you can always impose a concentration gradient, and you can measure the number of atoms passing through that thin film. So, it is very clear that J, which is the flux, is nothing but m by a t. So, we can write down I by a dm by dt. Okay. What is that? Let us look at it. So, this is the mass and time, because it is nothing but dm by dt. You see here, we can always write dm by dt. I is a constant here. Okay, dm by dt we can write down. So, dm by dt is nothing but a slope of this cup. Initially there is 0 slope, then there is a finite slope. Okay, sorry, there is a finite slope. So, that means J is proportional to the flux or the slope of this curve. Okay, that is the mass transport by time. So, we can actually put it down in very nicely, that this is nothing but J is equal to minus a constant and concentration gradient, because this one which I showed in the last class, this is nothing but a gradient. That is the gradient of the slope, is nothing but a gradient, okay, dm by dt. So, J is proportional to delta C, which is, or J is proportional to one dimensional del C by del x. Okay. That is the gradient here, you see here, slope. Anyway, so this is what is known as fixed first law, and J has a directions. So, delta C also has a directions. Diffusivity D is basically a tensor quantity, and this delta I is basically a gradient operator, and it tells you, if I write delta is nothing but del x del y plus del z in 3D, and you operate on a concentration. So, therefore, it tells you concentration gradient in 3 directions x, y and z. So, this is my first law of fixed first law, but this is basically the law of fixed. Okay. And this is derived from continuum mechanics or continuum approach. We are not using atomic jumps. Obviously, this can also be derived using atomic jump, this is there in the books. Now, something has moved up, I will explain it. Special case where the following conditions are true, suppose diffusion happens in only in one directions. Okay, we can always think of a 2D thin film and diffusion always happening in one directions, and D is okay. Let me explain what is D. D is a constant, it is known as diffusivity. Okay. Diffusivity is the ability of a material or atom to diffuse. That is what is diffusivity. More will come when you discuss about the other laws. And when a D is constant and in isotopic medium, we can always write down Jx is minus D del C by del T at some time and some space. Okay. That simplifies our life because we can actually use a one dimensional format of the equations. On the top of the above simplification, you can always write down, okay, so this is x, always write down steady state. Steady state means suppose I have done an experiment after a long time and things have reached a steady state. A steady state means that there is no change of time or there is no effect of time on the concentration gradient. Then we can write down Jx is nothing but minus d del c del x. Del has vanished, has become d, because x c is only function of x, no longer is a function of x and t, because t is we have actually done the experiment for large time, infinitesimally large time. Now therefore things has become stabilized. So temperature time has no effect, only the space variable has effect. That is why we can write down this. This is a very simple equation, we can integrate it very nicely because we have del c by del x, sorry, dc by dx, and at any location x equal to t, x equal to x not t. So this t equal to t prime vanishes the moment you assume steady state. These are all assumptions we are going to make when we develop our phase transformation rate theories. Okay. So yeah, here it is showing how what the steady state. Steady state means concentration of a diffusing entity at a given location does not change with time. Suppose if you have a this is thin metal plate, you have a gas pressure as P1, gas pressure as P2. So this is the way diffusion will happen, gas atoms will diffuse through this. It is just like a porous membrane, and you have a gas in one side as high pressure, other side as a low pressure. So there is a concentration gradient, and because of that diffusion will happen. This is passing through area A. And if I plot in one dimension, because we can always assume this is happening only in x directions, this is what will happen to the concentration difference at x1, that is on this side, at x2, that is on this side, and there is a concentration gradient. You can see here del c del x is present, but this does not depend on time. This is completely steady state thing, so that is why it does not depend on time, and we can use that flux is equal to minus dc dx. This is what we actually used to see, all metallurgists or material scientists, we used to see such a kind of things, such a kind of derivations of the flux. But this derivation comes after making certain assumptions, and we always assume it's isotopic medium. That means physical and chemical properties of this system, the thin metal plate does not depend on the crystallographic directions. It is all same. It is an isotopic system. Therefore, in isotopic material, diffusivity constant d is also independent of the crystallographic directions. In other words, this is a scalar quantity. D becomes a scalar quantity because t is independent of time, independent of composite directions or x, y, z, anything. So therefore, it is a scalar quantity. We can treat actually as like a scalar quantity. It is not a scalar quantity, and we can also integrate because this is a differential form of equation. Integration is required very easily and get the total flux and all this stuff. Okay, now just to explain you what is gradient. So you know what is gradient. If you are looking at a waterfalls, okay, and you know that the water is falling down the slope. So at any locations, suppose this is a location, this is one gradient here, this is another gradient there, because we are taking slopes, but water is passing through this. So obviously water will always pass through this steepest gradient directions. That is normally the case, because energy can be reduced largest if it is flowing in the steepest possible direction. That is why you have waterfalls, that is the main reason. So, direction of the decrease, direction of fastest decrease in the height is what dictates the diffusion directions, same as like here. So, that is why the saddle point concept is very important, okay, because that is why the saddle points barrier can be reduced extensively. Okay, so this is the first law of or the diffusions. Diffusivity or diffusion coefficient d I have already told you it is a constant, but it is not a scalar quantity all at the beginning, which is basically tensors, but we can always assume in one dimensional case isotopic medium to be a scalar quantity, treat them as a like scalar quantity. Negative sign for an isotopic material, diffusion flux is exactly opposite direction, in the opposite direction of the constant gradient. That is why it is a negative sign, because diffusion happens always in opposite direction, opposite to the down the constant gradient. So, that is what is happening, constant gradient is reducing from here to there. That is why we have to have negative sign to obtain the flux. Okay. So, I already explained you this, just to tell you that this is the fixed law. We can always do a simple maths, and del C by del x can be written as a C2 minus C1 x minus x2 therefore, in a macroscopic scale we can write down the fixed first law as j equal to minus d, the constant difference divided by the distance, the difference of the distances x and y. Okay, so let us not spend more time on that. We will get back to in the next lecture the fixed second law and how to solve these different aspects and how we can actually explain different phenomena which you observe in the real experiments.